Okay, I think we're ready to go. So this was the exact order of the exam, and then my TAs had me reorder the questions. The hardest one was first, and they thought that that was dispiriting. Is that the word? Disheartening? I don't know. That it would throw you in a funk, so it's now out of order, but it's the same content, right? So in other words, start with the first question and work towards the last one. Okay, that said, these are literally the exact questions off the test, right? It's the exact same content for each one of the questions. So if there's anything that's unclear here, it's going to be on the test on Friday. So what can I clarify? Yeah?
Can you go through the second one? How to calculate attractive force for monovalent, divalent, trivalent?
Sure. So if you've taken, who's taken physics like the first level of college physics? You've all taken that before this class, or you're taking it now? You're taking physics 2, electrical magnetism or whatever. So you've already taken this one, Coulomb Attraction. So you definitely should have seen that the attractive force, if it's a Coulomb, right, Coulomb Attraction is K, I think they use the terminology Q1, Q2 over R squared. This should not look brand new to anybody, I hope, in this class. Oh, you're doing it now in physics 2?
Yeah.
Oh, awesome. All right. Well, F is the attractive force as opposed to the repulsive force. So this is the exact same thing that we do. We just use slightly different letters, right? In our class, we've talked about it like this. K, instead of writing out K, we typically just write out what it's equal to, which is 1 over 4, brain's not working, 4 pi times the permittivity of free space, which is equal to what? This is 8.85 times 10 to the negative 12. What's our units on that? Is it coulombs per meter? Is it coulomb meters, coulomb per meter? Am I jacking it up? What is it? Oh, it's farads per meter. Scumbag farads per meter. All right. So that's K. That whole thing right there is K, right? And then instead of Q1 and Q2, because in physics you could be calculating whatever arbitrary charge you want, in this we're talking about ions, and ions come in units of integer electron charges. So all we do to modify this is we make it the absolute value of Z1, that's the charge, the oxidation state of Z1, times the absolute value of Z2, the oxidation state of the second ion, times the fundamental charge of an electron squared, right? Divided by the separation distance squared. That's it, right? It's the exact same thing, except that in physics it's a little more general because you're talking about whatever arbitrary charge difference you want. And here we're talking about ions that have integer values of charge, right? So if you were going to do the example I said here, could you calculate it for monovalent, divalent, trivalent? Sure, we could plug those in. Let's do it for monovalent first. If this is a monovalent ion, then somebody calculate 1 over 4 pi epsilon naught. Somebody plug that in for us. By the way, while we're chatting about it, do you all use a calculator that can do units? And if not, why wouldn't you? Why wouldn't you do that? I bought this 20 years ago and it's $50. It's probably less now. Like any TI-89, I don't know what they call them nowadays with your newfangled calculators, but I guarantee for $100 you can get a calculator that will do everything in units. It'll do derivatives and integrals and give you the appropriate units as you do those things. If you've never seen this, I've foreseen this amazing thing that college students aren't using the best tools available. And I've put content up on the top hat. So if you go to the very end, there's the worked homework stuff. There's also this thing, which shows you how to do unit conversions, how to create your own custom variables that have custom units and then use those, how to calculate all sorts of things, solving multiple equations simultaneously with units, doing integrals and derivatives with units. So what's the most, who has a TI-84 nowadays? Who has something else? Can a TI-84 plus do units and all that jazz?
Specifically can't, because that's why it's allowed on like standardized testing.
That's crazy. That's crazy to me. Well,
so we can use
you can use any calculator except one that does Bluetooth communication on my class. If you want to do one that solves massive systems equations with units, why the heck wouldn't you? I use this every day as an engineer. Why are you doing it in your head? Anyways, if you want to see examples of how to do that, this is actually done with an emulator. So you can all download the emulator and do it on your laptop. You can't bring that to class for a test. So I would suggest buying a calculator for your test that can do this because you'll use it for the rest of your career, right? It's $100. $100, and you think how much money you spent for tuition this semester. This will save you oodles. Anyway, that's just my opinion. I do not own stock in TI. I have no vested interest except that I think it's insane for you to do this on your own. Okay? So I've done lots of videos on how to do this, and it's pretty amazing. That said, if you want to do it the hard way, we can do it the hard way, right? So let's plug in these units, right? We want to end up with the units of force, which is going to be newtons, right? And right now, let's plug in everything with units and make sure that we cancel it out correctly, okay? So what's 1 divided by 4 pi epsilon naught? 8.99 times 10 to the, positive 9? And that's going to be units of meters per farad?
We don't have those calculators.
Well, I mean, but you see this was in the denominator. You divided by farad meters, so now it's in meters per farad, right? Y'all with me? And you should definitely get those calculators. By the way, Wolfram Alpha can do a lot of that. Not all of it. It can do a lot of that with units. And it's free to use. Okay, what's the charge in a monovalent system? We're talking about a monovalent cation and anion. This is something like salt, sodium chloride, +1, -1. Epsa?
Question about the E squared?
That's E squared. That's the fundamental charge. That's the charge of an electron. We're going to write it out what it means in just a minute. Yeah. That's the charge of our two ions. I'm going to give myself more space real quick. Okay, so that's our prefactor. That's K from physics. So Z1 and Z2, that's the charge of the cation and the charge of the anion. And then we're going to take the absolute value, so you don't need any negatives or anything. This is all positive numbers. Okay, so that's 1 and 1 if it's a monovalent system. 1 times 1, could have just left it out. What's the charge of an electron? And that's coulombs per mole, right? We square that, okay? We're going to divide this whole thing by some distance, right? So in order to calculate, when I say how do you calculate the attractive force, I'd have to give you a separation distance, right? Otherwise, all you could do is report it as a function of r squared, because we don't know what r squared is. And the only way you can figure out what the equilibrium distance is if I give you b and n, right? N is almost always 8. Right? But b is just some constant. And if I haven't given you that, you can't solve this. Right? So let's just plug in r for now. R is going to be the units of meters. Something length. Nanometers, meters. It's going to be something length. Okay? So let's just do a quick unit analysis. If you do this, what's a Coulomb equal to with farads? Somebody help me with that. Coulomb, farad, conversion. What is that? A farad is a... And we're going to have to turn it into newtons at some point anyway, so let's go ahead and throw newtons into that.
If you Google Farad SI, I think it gives you a nice table.
Farad SI, Wikipedia saves the day. Let's find it. This is why I would just get software to do it for you. So we want to get to newtons, right? So we're getting there. Coulomb squared per newton meter is a farad, okay? Those seem like the units that we want for this problem because we want to end up with newtons. We've got coulombs and we've got meter squared. So let's replace our farad with coulomb squared per newton meter. Yeah?
Are you going to give us the conversion factors on the test?
I give you some basic ones. I'm assuming that you guys have been solving homeworks with this stuff. So if you put whatever you need on your note sheet, all that I've got on the test is some really basic stuff. So if you need it, put it on your note sheet. Okay?
So like this, we should put this farad to...
I would put that on your note sheet. Yeah. That whole line, if you want to. I'm going to right now just rewrite this. That farad, we're just going to recognize that that is equal to a Coulomb squared Newton meter squared. Okay? All right? Sorry. Coulomb squared Newton meter, not Newton meter squared. Okay? So now, do the units cancel out here? And do we get the right answer in the end here? Well, farads in the denominator, so we can just switch all of this and then put it up next to the meter. Right? So let's just rewrite this just so we're not confusing ourselves. Right? I'm just going to write units for a minute. I'm going to leave out the numbers. I'm just going to write units. We've got units alone gives us meters times meters Newton per Coulomb squared. That's going to be multiplied by Coulomb squared over, if we put R in as meters, then our meters cancel out, our Coulombs cancel out, and all we're left with is Newton. So if you plug it in exactly as it is now, assuming that you put R in as meters, your answer will come out in newtons. Newtons, which is the appropriate unit for force for atom interactions. Okay? Everyone square on units? You'd be amazed how, I'm not joking, huge amounts of points every year are shed because of units. So do what it takes to figure out, remember how to do newtons. If you want, the TAs are good at this. They can walk you through this stuff, but make sure you can do units for all the sort of questions that are listed on the study guide. Okay, so when you plug this in, we'd have to know an R value to get an actual value. Otherwise, it's going to be something as a function of R.
So it would be given an R value.
Yeah, if I was asking you to calculate a force, I would have to give you an R value. I'd say if the separation distance is 2 angstroms, what would you do? You'd say that, well, an angstrom is not a meter, and in order to get newtons, which you ask after, this has to be in meters, right? So convert angstroms to meters. You remember that an angstrom is 1 times 10 to the negative 10 meters, right? 1/10,000,000th of a meter. 10. An angstrom is 1 times 10 to the negative 10. A nanometer is 1 times 10 to the negative 9. A micrometer is 1 times 10 to the negative 6. Meter, negative 3. Millimeter, negative 3. Learning how to use the SI units, like the prefixes, is just worth your time now, because it's never going to go away. You'll be doing it for the rest of your college and engineering career. Okay? Any questions on this? How would it be different if it was a divalent ion? 2 and 2 instead of 1 and 1. What if it was something like MgCl2, magnesium chloride? What do? Now you've got a +2 and a -1. Just do 2 and 1. Yeah. This is just an approximation. This is pretty close, though.
So that Z1 and Z2 is just the oxidation state.
It's the oxidation state of your cation and your anion, respectively. And you take the absolute value, so it doesn't matter if it's positive or negative. It's all going to be positive once you plug it in. Any questions on this? Is straightforward? Yeah. Do you have to multiply it by what now? Oh, no, you don't. No. Remember, these are approximations. There's much more sophisticated ways for calculating energies that we're not going to get into in this class. Something called density functional theory. It's a way of calculating atomic interactions at a much more precise level. This is to approximate things, to give us approximate energy depths and stuff. What else? Are there any questions on this? Should we move on? Yeah, question?
Yeah. The next question, how does average interatomic spacing from equilibrium ion spacing? What is that?
Okay, yeah, we chatted briefly about that in class today. Oh. Okay, so we chatted a little bit about this today as we were talking about the ceramic knife expanding. Does it do it more than the regular knife, less? And we drew this diagram. Well, we pulled up this diagram from Chapter 2. The old energy versus interatomic separation diagram. And for whatever your material is, it might look something like this. Right? Where this is E naught. And we talk about a binding energy. It's very common where people will say, like, the binding energy for this compound is 4 electron volts, 2 electron volts. Realize when they say that, they're talking about a negative 2 electron volts, or a negative. Even in the book, in Chapter 2, in the table in the book, it lists all these compounds and their binding energy, and it lists them as positive values. Realize that they got that by, it's this negative axis, right? So don't get confused on your units. This is going to be some negative number, okay? And when is it actually occupying this state, did we say? Well, yeah, when the separation distance is R naught, you're right. Right? When the separation distance is R naught, its average is this point only at 0 Kelvin. Right? I mean, if you cool this thing all the way down, atoms are always vibrating, right? That is thermal energies. They're vibrations, right? So if you cool them down, they no longer vibrate, meaning the distance between them is fixed. At any other temperature than 0 Kelvin, they're vibrating, meaning the separation distance is changing. They're rocking back and forth. If it's a low temperature, they're rocking back and forth a little bit, right? Maybe at a low temperature, at temperature 1, it's rocking back and forth like that, right? And so the average position goes between this point and that point. So it's just a little bit to the right. It's expanded, but not very much. Let's say you heat it way up. You heat it up either with a laser, you blast it with a laser, or you put it on a stove, or whatever you do. You heat it up, and now it's got lots more thermal energy. That means that it's rocking back and forth between those 2 points. That make sense? More thermal energy, and so the average position is right in the middle, right? It's spending time anywhere between here and here, but the average is right there. So it expanded. It went out. It got bigger, right? Expanded. So when I say what's the difference between equilibrium and average, that's what I'm talking about. At some non-zero temperature, you got to realize it's occupying kind of all these points because it's vibrating at actually a pretty high frequency, and that its average position is typically larger than its equilibrium position, but there are exceptions. There are materials that shrink as you heat them. They're just goofy, and it's not the rule.
So how would you calculate it?
What?
That's the second part of the question.
Okay, so how would you calculate what? The average? Okay. So if I said you heated something up and it oscillates between this point and that point, what would be its new average bond distance? It's just the halfway point. Yeah.
So is there an equation for that, or do you just...
Nope. I mean, if I tell you this value and that value, you can tell me the halfway point pretty easy.
Yeah, sure.
Add them together and divide by 2 is your equation. Yeah.
Kind of like an example question. Just like we talk about the difference, meaning that like.
So there's a much harder question coming on the test, but you need to know this concept to answer it. Okay? How would you go between these energy levels, right? How could you solve for the... If I asked what is the radius at which you have some specific energy, how could you do these things? Or vice versa. How could you, at some radius, what's the energy at that level? Right? If I say you stretch something out to 10 times its original bond distance, right? You really stretch it out. What would be the energy at that point? What energy would it take to get there? Right? So if you say from 0 Kelvin you're here, and I stretch it out 10 times, you need to take 10R, plug that into your energy as a function of R expression, and tell me what the energy is, and then take that difference and say, oh, it took 2.5 electron volts or something to stretch it out. You guys see what I'm getting at? I've told you the question, basically. Everything. Are there any questions on this? Now is the time to ask. Yeah, Clarissa.
So if you're in like 10R, is that like the average that you have to divide by 2 in order to like get that energy point, or is it like plotted on the line?
What, for example, let's say this is the question. If I said, what's the difference in energy? What is delta R between R naught and 10 R naught, right? The equilibrium separation and 10 times that. How would you go about that? Yeah, question?
You mean delta E?
Oh, I'm sorry. Thank you. Good catch. That should definitely be delta E. What's the difference in energy? Thank you. So how would you go about that? Ebsa?
Are we given a function in terms of R?
Yeah. And if I don't give it to you, then you know what it should look like. It should look like this. Energy as a function of R is equal to negative A over R plus B over R to the N. You know how to solve for A, for a monovalent, divalent. We just figured it out, right? A is everything in this expression except for the R part, R squared part. All the rest of that is A, right? B I would have to give you. N I would have to give you. But once you have that, remember that E is a function of R. You can plug in any R value you want and get an energy. So you could plug in R naught and get an energy.
And then can you just say 10 R naught?
You could plug in 10 R naught and get an energy, and you could take that difference. And that's delta E. That's your difference in energy. Okay? No surprises on this midterm. I don't want anybody saying it was a surprise. Yeah, Absa.
So is that the negative A and B the coefficients of the ions from the Coulomb energy problem? Is that the Z or whatever?
A and B? Yeah. A and B, so right here, all of this stuff, that equals A. Or in other words, all of this stuff right here, except for the R squared, equals A. That's the constant A, which sometimes we give it to you on a problem. We say the constants are A is this, B is that, N is this, and I have you do some geometry. This is where that A comes from. From like a physics standpoint, this is what A ought to depend on.
But just without the R, right?
Well, yeah, because in our expression, the energy, now remember this is for a force, that's why it's over R squared, and it's a positive term. In energy, we take the integral of that, and that's why it's negative for one thing, and it's not R squared, it's over R. But that's the same A. The same exact A. Yeah. Chase.
Was this the equation where n was like 8, like a bunch of times?
N is, in my class, it's almost always going to be 8. Turns out that that's a pretty good approximation of real life.
What is that?
N is an exponent. N is right here. Oh, it's a fitting parameter. So this expression here, it approximates real life. In real life, when you have two atoms that interact with one another, the shape of that interaction is like this. It goes down steep, and then it's like a more gradual rise. And the way that you get that is by adding together the attractive term with the R squared and a really negative term. That's why it's n to the 8th power. It's really strongly negative, but it falls off quickly because it's a high exponent.
So for this class, we should just keep that n as 8.
Assume n is 8 if I don't tell you, but it's going to be 8 for the midterm. But it can be other values. There's lots of other classes that will assume a slightly different value. Yeah, I don't know your name. Victor.
So for our Z values, if it's monovalent or divalent, can we have a 1 and a 2, or like
Yep.
the same?
What do you mean they're going to be the same? If it's a monovalent compound like sodium chloride, then Z1 and Z2 are both 1. If it's a divalent like magnesium oxide, Mg2 plus and O2 minus, Z1 and Z2 are both 2. What do we care about the fact that its oxygen is minus 2? No, we don't care because we take the absolute value. So it's still 2 and 2. Yeah.
That just reminded me of a question that I actually had about the previous one, where it asked for it asked how you calculate it on monovalent, divalent, and A. There was on the previous question.
Yeah, trivalent.
How does that equation change based on the? I just knew that.
How does it change based on what now?
On those ionic pairs.
The Z value changes. If it's sodium chloride, you use 1 and 1. If it's magnesium oxide divalent, you use 2 and 2. If it's aluminum nitride, then you use 3 and 3. Yep. Everyone good? Yeah.
So that whole thing is, if that whole thing is A,
That's A.
do you give us, you said you always give us, you usually give us A and B, right?
In the question on the midterm, I'm going to have you calculate A, and I'm going to give you B. And N. Yeah, in the back.
So what if the Z value is like 3 and 1, so it doesn't count as anything of like a metal divalent?
You would use, if the cation is 3 plus like aluminum oxide is, aluminum is 3 plus, oxygen is 2 minus, you use 3 and 2. No, that's a mixture, right? It's a trivalent cation, a divalent anion. Was that clear, your question up in the back, in the blue shirt? Yeah. All right, what else?
So for the energy with respect to our equation,
Okay.
that's A, is the B over R to the N, would that be considered kind of like the experimental component, like what we had in the games for the energy?
Sort of. No, that's maybe the wrong way to think of it. I like where your mind's going, but that's maybe not a good analogy. All it is this expression is just meant to, it mathematically looks like what we observe in nature. We call this an empirical expression. It looks mathematically like something, so we use it as a model. The first part of it we have physical first principles that explain why A is what it is. We know Coulomb's law, and it turns out to be a really good approximation for this value A. But B and N, we just pick stuff that makes it fit. It just makes it fit the experiment. Yeah, Ryan? What are A and B? They are values that have appropriate units to get the appropriate unit of what we're trying to measure. In this case, energy. So the units of A need to be something energy times a distance because we're going to divide it by a distance. Yeah. To what A is? Yep. Yep, right here.
Just a quick clarification. You say we need to know the physical meaning of the equilibrium bond energy. There are a lot of things. So would that mean that just at R naught, the net force is 0? Is that?
That's an important part of it. So, for example, the only way that we can solve for R naught is by recognizing that it's when the force on it is nothing. If there's a force on it, they'd keep moving. They'd get closer, they'd get further. But when there's no force, they're going to stay put at absolute 0. That's part of it.
So what are the other parts that would be important, like for that,
That at absolute 0, that's where it stays put. Yeah.
like temperature absolute 0?
Yeah. At absolute 0, it stays put there. Other questions about it? You might be making this harder than you need to at this point. We've definitely covered what's on the exam on this, which is good. It's okay. If you got more questions, we'll keep answering them. But we've used a quarter of our time on one small part. Yeah.
So are we going to have to solve for R naught?
Yeah. Solving for R naught is something I think that I expect you to do on this. I think you solve for A. I think I give you B and N. So if you plug that into your energy expression and you take a derivative, you've got force. You set that equal to 0 and solve for R, and you've got R naught. If you've got R naught, you can plug it into energy. You can figure out E naught. If you're taking a difference in energy, you can plug in some other value and take the difference. Right? Okay, maybe for the sake of time, we should keep going. What else can I explain? Yeah. Lauren? Rachel. Yep. Well, so which one of these in particular are you talking about? Are you talking about right this one here? Okay, let's do those two separate. Those are two different things. So, like, what's a basic battery chemistry? All batteries are redox reactions, so let's just look one up. I don't know. Let's see what Energizer.com has for us. All right, right here. Let's take I think this was on our first, actually, homework, wasn't it? Let's do this one instead then. Right here. No, this one, that shows our two reactions. Let's show something else. Let's pick a different battery. Zinc manganese, zinc carbon. Let's do zinc carbon. A zinc carbon battery. If it's a battery, then it's got to have... Okay, here we go. So they've already broken it up into anode and cathode for us, right? Those are our two half-cell reactions. If we combine those together, that will give us the entire reaction.
So I guess my question is, if that's all we're doing, we don't have to do like the more like more chemistry like balance, where you have to like take into account if it's like basic, no?
What other balance are you talking about?
I think that that makes sense.
Well, for example, if I gave you this, if I combined these two together, would you be able to separate them out into half-cell reactions? And how would you do so? What's the key to doing that? If I give you the overall reaction of a battery, how do you split it up into two half-cell reactions? What's the trick? Yeah, it's all about writing the oxidation state above each element and seeing which one's changed. The ones that they add electrons, right? Reduction is gaining electrons. They were reduced. That's your reduction happening at the cathode. And the things that lose electrons, is oxidation. That's happening at your anode. Zoe?
Are you going to give us the sheet of all the
Yeah, on the exam, I do have you calculate an overall cell potential. And so I provide the table like that we've been using in the book. So I provide you this thing. Right there. I provide something like this, so you don't need to put that on your note sheet. I've got that for you. Landon?
The overall potential just being like the delta V equals delta V naught minus RT over NF after log of the concentrations.
So remember, due to an unfortunate naming, overall cell potential is actually delta V naught. It is not delta V. I didn't name it. I would have called the other one overall, because it sounds like you're done.
So what is the other one called?
They call it the cell potential.
Cell potential versus overall cell. Okay.
Yep. I didn't name it. Yeah.
Just testing question. We're allowed to have the periodic table in addition to our one sheet?
Yeah, you can bring your periodic table. You don't need it. Everything that you need should be provided, but if it helps you and you want it there, it's fine. You can bring it. And then you get one sheet of paper. You can do front and back. You can print it on there, or you can write it. I don't care. Eric?
Do we need to convert between delta V and delta G?
Yeah. On this test, I don't know if you need to. Is it on the study guide? I don't remember if that's on there or not. I don't think that I put a question on that. But if you wanted to, it's straightforward. You would just go back to right where we were, and delta G naught is equal to negative NF delta V naught. But that's not on the midterm. Other questions people have? So sorry, Rachel, I think we got lost. What else did you want to know? Yeah, so we're going to do a full redox reaction, which means we're going to have to split it into half cells. You're going to have to make sure that the electrons add up correctly. The same number of electrons involved at one half cell, since they travel through your device over to the other part, they have to be the same number of electrons over there, so you have to make them balance. Okay. Everything that I'm going to test on will look like something you saw on a homework. There will be nothing out of left field. Okay? What other things can I talk about? The bond separation, what's that? How do you determine equilibrium bond separation? Oh yeah, right here. Okay. So if you know what E is given by this. E is equal to negative A over R plus B over R to the N, right? That's your energy expression. Let's assume that I either gave you A, you solved for it, and then I gave you B and N. So you've got everything except, so you have energy as a function of radius. How would you get to equilibrium bond separation? We just said this. How do you do it again? Somebody summarize it for me. Landon, what do you do?
So you take the derivative of that to achieve force.
What's the derivative look like?
So you have negative A, positive A over R squared minus B over R to the N plus 1.
N times B over R to the N plus 1. Right? If you don't remember how to do that, just write it down. Right? If you're like me and you did calc and then you never looked back, just write it down. Or for heaven's sake, spend the $100 and buy a calculator to do it for you. Okay? So now you got force. How do you get to equilibrium bond separation? Set the force equal to 0. That's when it is in equilibrium, when there's no net force on it. So at F net equals 0, we have R equal to R naught. So when you set that thing equal to 0 and you solve for R, you will have R naught. Alternately, I would write on your note sheet, because you did it on your first homework, that R naught equals, what is it? Let's pull it up. Oh, homework 1. Yeah, it's N times B. Oh, right here. A over BN. Oh, no, I've done it. Is that too hard? Anyways. A over BN.
Before he solved for R naught, he just plugged, he solved for A and plugged that back into the force equation, and it was a lot easier algebra.
Oh.
The algebra gets really messy
Yeah.
if you
Okay.
try to do that way.
Yeah. So whatever you want. Whatever's easy, figure out how to do it and not waste a lot of time, because realistically, you've got 3 questions on this exam, so you've got 15 minutes per question, and each one's got at least 3 parts, which means you got 5 minutes per part. So you got to move. They're not all calculations, but your time will be of the essence for sure on the exam.
So in the original equation, is that first R under A?
Same R. Yeah. Yeah, same R.
Is that B sub n or B times n?
Which one?
R naught equals A over B sub n or B sub n?
Oh, B times N, right here. That's B times N. Good question. What's your name? Jin Chung, what's your question? Yeah. Yep. I don't know your name. Pramit. That's not on the test, so I'm not going to do that because our time's limited and it's not on the exam. Yep. There's one in the homework if you want to go back and review it, though. Yeah. I really hope that you can do this right there, that you could then plug in any R you want into the energy expression to figure out an energy, that you could take the difference between those. That is the first problem. Well, now it's the third problem, which we thought was the hardest, but I think at this point, it's not going to be hard. Right, Landon? Yeah, are there other questions? Ebso, what do you got?
We have to know the congruent, incongruent melting.
So, incongruent melting, what's the difference between incongruent and congruent? That's not on the test. We talked about it very briefly. Let me just say in like one word what it is, in one sentence or two. Yeah, or two. An incongruent versus a congruent melting can be seen pretty well in this right here. A congruent melting compound goes from one pure solid to one pure liquid without changing composition. Do we see that happening? How about right here? This line compound turns into a liquid at that without changing composition. It also happens right here. Right? This compound turns directly into a liquid. There's no two phases involved. But this thing, it goes from a solid with some composition into a liquid with this composition and a solid with that composition. So this would be incongruent melting, and this would be congruent melting. In other words, all paratectic points, because this is a paratectic point, are incongruent melting. That's more than I wanted to say. Yeah. Question? That's usually, but not always true. If you just did homework 3, hopefully you found that there's an example where two of the lines, they look pretty straight up and down, but they weren't line compounds. So there's exceptions to that rule, but most of the time, if it's a straight line, it's a line compound. You should be looking for reasons to disprove it. Abigail?
What is the physical meaning of equilibrium bonding?
Equilibrium, so that's this value right here. At equilibrium, R naught, it's this value of energy, E naught. That's what that is. Carlos? Yeah, are we good to move on from what we've seen? Okay, let's keep going. So Hess's Law. How did Hess's Law work? Okay, oops. All right, somebody describe Hess's Law for me. Do you remember it? Lana, what do you think it is?
The total change in energy is the same regardless of how you got there.
Yep. Yeah, the total change in either energy, enthalpy, or entropy for whatever reaction you want, if you could break that reaction up into a series of smaller sub-reactions, it's the same. If you add those up, it's the same as doing it in one step. So I think the Wikipedia page has a pretty good entry on this. So right here, okay? So here they give you those series of reactions, okay? And then they want you to find it for this reaction. So what Hess's Law says is that you can take, if you want to get to this, you can add together those 4 reactions in some way such that this is the end result. And once you do that, whatever you did to those, whether you reversed them or multiplied them, you take that delta H and you multiply it, or make it negative if you reverse it, and add that together, and that's Hess's Law. Okay? So on this one, what did they do? B2O3 is in that first equation, so you're going to have to flip it, because it's a product here, but it's a reactant up there. So you're going to flip that first equation, meaning instead of being positive 2035, it's going to be negative 2035. What else? Boron is a reactant, and it's a reactant in this fourth one. If you add the first and the fourth, do you get that? No, because you got water and stuff.
If like we got this question, would we have like the final equation, or would we?
Yeah. Or maybe I would describe this in words. Maybe I wouldn't write it out. I think that's what I did on the midterm. So you can write your own, and then you've got a bunch of sub things. You have to put them together. And if you just add 1 and 4 together right now, it doesn't work because you've got, you've got that B2H6, which ought not be there. Well, that's actually going to cancel out. So it's just like, it's the H2O3 and the hydrogen. So anyways, you have to use all 4 of those equations. Yeah. I'm forgetting your name. Lauren. Yes. If for some reason you decided that you needed to multiply one of these by a number, like you need to multiply this by 1/2 or whatever, then you also multiply this number by 1/2. If you flip it, then you make it negative, and if it was negative, you make it positive when you flip it. Okay? I don't know your name. Ben.
There was one of these calculations where you said we don't multiply that number by.
That's for delta V. Yep. For entropy, enthalpy, and free energy, they all get multiplied. For voltage, it doesn't. That's like it's a material property. It doesn't change with the amount of substance. It's dictated by the material itself. These all depend on the amount of substance. That's why they're a per mole basis. The other one's a voltage. It's a material property. It's not a per mole basis. Yeah.
Does the delta V still get flipped?
Yes, it does get flipped. It just doesn't get multiplied. Okay? I don't remember who asked this initial question, but how do you feel about Hess's Law? Are you able to do it? I would suggest you work some of these out, and if you're stuck, and if you're not able to get it, shoot me an email, and we can figure it out maybe a little bit better. Ryan?
On the chart that has like the different.
The reduction potentials? Yep.
So what's the second value that you want?
The second value?
Don't they usually give you 2?
Nope. I don't think so. They typically look like this. Something turning into something else. If it's a reduction table, it's something plus an electron turns into something else at some voltage.
Oh yeah, it's actually there's different chart. The one for
For the what?
delta H.
Oh. Okay, so the other one that we looked at in class was this one. Energy formation table. I mean, in class we saw things kind of like this. That's not a good one. How about this? Yeah. For example, on this one, as a function of substance that we're looking at. Oh, gosh. Google, why? Anyways, you can see there's like a delta G formation. There's also the enthalpy. So it might have entropy, enthalpy, and free energy. I don't think you're going to have that on this midterm. All right, what else can I answer? Premit? What's your question, Premit? Microstructure. Are we ready to move on from Hess's Law? Okay, let's do microstructures. Microstructures. I don't remember where it is. All right. So when you draw phase diagrams, one of the most valuable reasons that we use phase diagrams is because they tell us how much of different phases there are, when they exist at different temperatures, and how you can manipulate them to get different structures. So let's pick a horrible phase diagram and do a microstructure. What will happen if I put horrible phase diagram? What do you got, internet? I just saw one go by. Water's no, water's not so bad. Where was the one just back a page? This one here. This looks horrible. That looks horrible. That one is the one we want. Is it going to be big enough to do, though? Maybe? That is bismuth and tellurium phase diagram. Okay. That is a horrible one. Okay, something like this. Snag it. Okay, on this one, if we cooled it down from a liquid, what could we expect to see? So let's pick a composition where we want this to do this at. Okay? A really easy one would be like this, 90 over here, the eutectic. You cool that one down, you get the eutectic structure, easy peasy. What if you cool down in between these two? What are you going to get? Right in the smack middle of those two. What are you going to get? Tell the person next to you, what do you think? Okay, what do you get? Well, you've got a reaction there at 562 C. What do we call that reaction along that line? That is a paratectic point. At 562 and at this composition of Bi4Te5, right at a 56 or something, that is a paratectic point. So what does a paratectic reaction mean again? It means that you've got a solid plus a liquid turning into some other solid, single-phase solid. That's a terrible beta. That was supposed to be a beta. It was real bad, right? So as we cool down, just above this line versus just below, how will it look different? Let's draw the one just above. Above versus below. Well, above, let's zoom in a little more. We could do the lever rule, right? Just above. Oh, yeah. Question, Clarissa, and then Eric. At the paratectic point, that's what happens. We're over here, so we don't have that. But this reaction, even over here, will happen. If we call this phase alpha right here, and this is liquid, at this point, we will have some alpha and liquid. And all of the alpha and liquid will turn into beta, according to the paratectic reaction. Sorry, not all the alpha, you're right. Until the liquid is consumed, you will form beta. You're right. You will have your pro-paratectic alpha left over. Yeah. Good. That's a good catch. Eric, same question? Okay. So just above this point, we could do the lever rule, and I could have you sketch it for me, and you'd say, okay, the lever rule will tell me how much alpha, this phase, we'll call this guy alpha. This one is going to be beta, right? So how much alpha is there? It's going to be this divided by that, right? I don't know what these values are. You could read it maybe off of there. 47 divided by 38 or 9, right? Divided by this total distance, which is going to be, I don't know what those units are doing up top, something weird. But assuming you could read these nicely, and on the midterm I've made it really easy because I've put little numbers on these so you can read them right off of it, okay? So you won't spend time wasting it reading plots. You could do the lever rule, though. Just eyeballing it, it looks like it's going to be about 80% alpha and 20% liquid, because it's about 80% along the line towards alpha, okay? And you could tell me the composition by reading it off of there, okay? So how would you draw that? It's 80% solid, 20% liquid, so that means that it's going to look something like this. You're going to have mostly solid with just a little bit of liquid. So here's all your solid sections. And those are the alpha phase that have a composition that you could read off the plot. So that would be alpha. You would say that it is 80 weight percent if that's it's in atomic percent. So that would be mole percent. Really jacking this up. And the composition of alpha would be equal to about 60 atomic percent tellurium, right? And you could label liquid in the same way. Everybody clear on that much on this step? So when you go below that line, any liquid that you had above there, that 20%, is now going to turn into a mixture of alpha and beta because it's between your alpha and beta phases. Okay? So if I would redraw my pro-paratectic phases roughly where they were, right? Color them in. Roughly how they were. And then you've got the lamellar sort of region in between, because it's going to happen very quickly. It's going to all turn into two phases. Okay? Any questions? Yeah, Ebza?
So in between it is that the entire thing is lamellar? In between
Everything that used to be liquid is going to undergo this reaction. It's going to turn, some of the alpha and that liquid are going to turn into beta. So technically, these islands should actually shrink a little bit. They probably would shrink a little bit.
We go process with the composition on there too.
Yeah, you'd want to label that with composition.
So in that case, the 80% is the composition.
No. You'd have to redo the lever rule. You'd zoom in on this again. Now it's smack dab in the middle, such that overall you have 50% alpha and 50% beta. You would do the actual math to do this, of course, the lever rule. And the compositions are different. The liquid is no longer its composition. Now, beta and alpha, you could read the compositions off the map. I think this was 60% and this was something less. Okay? In other words, when you draw these microstructures, they're not complete if you haven't labeled the amount and the composition of each phase present. Lauren.
Would the lamellar structure still form even though, like, you're only, in the alpha plus liquid, you're only forming beta, so, like, in there you drew new alpha. It's like, to make the lamellar structure, you have to, like, have more alpha form, but no more.
Oh, I see the problem. Well, we know that we have 50-50 after, but we had 80% alpha before, so you're right. That actually may not be quite as lamellar as it looks. It might be mostly beta in between, and your A's would shrink a little bit. Anytime it's happening at a single temperature, it tends to form a lamellar-like. It's much more dispersed. But yeah, that's a good point. We have 50-50, so the islands would have to shrink. Otherwise, we have too much alpha the way I've drawn it right now. This is actually a good example because I messed it up. Good catch on that. Tyler?
Is eutectic structure synonymous with lamellar structure?
Yep, eutectic, eutectoid, lamellar structure are all the same thing. Yeah, Ryan, then up front.
Where would we have the microstructure where they precipitate some heat in the middle, make the grain regions?
I can show you that. I don't know if we can on this one. Let's look and see. If OneNote responds. So on this one, I don't see a spot to do it because all we have are a bunch of paratectics. Just oodles of paratectics. Let's find the new diagram. Let's draw one, actually. So we'll draw just a eutectic, for example. What did you want to see again, Ryan? Where it's a...
What we saw earlier, where if it cools slowly,
Oh, along the grain boundaries. Okay, we need it to come from a solid then. This is being weird, though. Come on, OneNote. This is not letting me erase, which is strange. Let's try that again. So let's do it for steel, I guess. Okay? Steel looks like this. It's got a eutectoid reaction. It's got, this is your austenite phase. It's got this going on up there. Pen is not working. I think the battery's dying. So that leaves us with alpha plus cementite down here, Fe3C. You've got alpha here, alpha plus austenite here, austenite plus cementite over there. And we said that if you cool down in different spots, you're going to get different pro-eutectoid phases. If you cool down right here in the middle, you'll just get the eutectoid structure, right? Pure austenite is going to turn into a mixture of these other two. If you cool it down right here, just before that point, you're going to have pro-eutectoid cementite forming, and that will form along the grain boundaries. And the amount of it you could determine by doing the lever rule above that line, right? And then once you go below that, any austenite that you had, which was the bulk of the grains in that case, are going to turn into cementite and ferrite. Okay?
the microstructure is always formed when it goes from a liquid to solid, liquid solid to a different solid and liquid.
So no, not necessarily. In this one, we never heat it up to a liquid. When you process steel, the temperature to turn it to melt it entirely is really, really high. So you might actually just heat it up all in the solid state. You might heat it up to this austenite region, let it sit there until it's all austenite. You got a bunch of grains of austenite, and then you cool it down. And depending on, maybe when it's up in that state, you add or remove carbon. Like in a blast furnace, they remove carbon, right? They want to decarburize it a little bit, so they burn it. They basically burn it off as CO2. They blow hot air on it, and it burns away the CO2, and that moves it over. So maybe you were initially here, but you put it in the blast furnace, you remove some CO2, and then you cool it down, and you went from a hypereutectoid steel, a high-carbon steel, to a low-carbon steel, right? So we never melted it in that process. This is all can happen without melting it. Other questions, Sam?
So if you follow that first line you drew, the hypereutectoid, you follow it all the way down into the alpha.
Down here, yeah.
Yeah. What is that going to look like? Because you have that beta forming along the boundaries, but then it all has to switch over, right?
Yeah. I think my pen has died, which makes me sad. It's a 4A battery. It's the goofiest battery, and I just ordered some, and they're not here yet. All right, we're going to do it. Oh, there it's working. We got a little bit of juice left. All right, so in the austenite phase, let's say we got grains, okay? Just above that eutectoid temperature, we've still just got grains. Nothing's happened. But as soon as you go below it, it's just going to be, it might somewhat vaguely resemble the grain structure from before, but it's still going to be lamellar all the way throughout. Okay? And the amount of the ferrite and cementite that you've got, you can determine at any point by doing the lever rule. And the lever rule you can do at any temperature by just drawing a flat horizontal line and seeing where it intersects the sides on the left and right. What's your name? Chase. Yeah, real quick. Are there other questions about phase diagrams while we're here? Yeah.
About the last diagram. So
Oh.
we're doing the drawing that you have, that lower one. So labeling that, if we use the lever rule just on the lower part, so we'd label it as like 50% alpha, 50% beta, and then label the compositions of alpha and beta.
It's probably a better representation. So you would label both of them, and on each of them you'd label how much alpha, how much beta, how much liquid, and the compositions of them.
So is the composition just below the eutectic line, is that affected by the previous composition at all?
The composition just below, so there's no eutectic here. There's a paratectic line. So just below that, does the composition change? For this one, it doesn't. It's basically a line compound, so its composition doesn't. But before we had composition of a liquid, and now we're going to have composition of beta, and they're different. The liquid is clear over here at, what, 50-ish? But beta phase is at 55 or 6.
Okay.
They're just different phases.
So in the top one, we would label alpha some percent alpha, and then alpha is some percent bismuth and some percent tellurium.
Yeah, and you only need to say that it's how much tellurium. It's assumed that the other 40% is bismuth. Otherwise, it gets to be a lot.
So it's like alpha is 80% of that whole microstructure.
And its composition, C sub alpha, is something.
And then the liquid is the other 20% of
Right.
the thing, and its composition
Yep.
is 50
That's right.
something percent tellurium.
That's right.
Okay.
Other questions on phase diagrams and microstructures, Sam?
Is there any nice way to know whether a vertical line is a line compound?
The only way to do it that I know of is to do the 1-2-1-2-1 rule. Right? So take this one. This one's tricky because they left stuff off. First off, what's that dotted line? Dotted lines always signify uncertainty in these diagrams because experimentally, these are nasty regions to achieve probably, or maybe it's experimentally, it's really slow or sluggish. So they think that's what's happening. Particularly on that one, I think I'm almost positive what this is that these ones over here are thermodynamically stable, but kinetically you often just get this. You don't ever form these. Instead, this acts like one great big liquid plus this phase right here, beta phase, one great big liquid plus beta region, and this acts like all beta. And you have to let these cool for a long time to crystallize. That's why they've drawn incomplete diagrams here. I'm almost certain. I don't know. I'd have to pull up the paper, but I'm pretty sure that's what this is. Dashed lines mean uncertainty. It means it was hard to measure. We think it goes right here. What other questions do you have about this, Sam? You asked something else. Was there something else there?
It was just, like, besides just one-to-one logic, like,
Oh, Okay, so let's ignore this dashed line for a minute. If we did the 1-to-1 rule, there's a problem. There's lines that are unconnected. So I won't give you that on a test, because you can't do the rule when there's disconnected lines, right? So let's pick a different phase diagram where they're connected. This one's horrible. Let's pick a different one. Oh yeah, exactly. See? Do you see the difference between these two? This is what it ought to be thermodynamically, see with all those phases, and this is exactly what I just said it probably is. In practice, all these intermediate compounds are sluggish. It's hard to get them to form, probably because they're really ordered. You got a mixture of bismuth and telluride. They probably make like really intricate layering, bismuth layer, tellurium layer, something that takes a long time to get everything just so. When it's slow, the odds of it not happening are pretty good. And so instead you see this experimentally, and you don't even see those intermediate compounds. It might be a lot of work to actually make it so you see those intermediates form. So that one we could label. Let's label that one. If I gave you this one on a midterm, you could label it easy peasy, assuming it's not broken. Let's see. If you're going to label this one, well, they've already labeled it for us. Let's make sure that it works, right? Assume none of those labels are on there. You know that up here is liquid, so that's your single phase. Pick any temperature, draw a line across it, and it can do the 1-2-1-2-1 rule. So we got a single phase, so this must be a 2. So that's going to be liquid plus, we'll just call it alpha. That means this is an alpha region. This is a straight line, so we're going to think it's probably a line compound. That's our initial assumption. Here, I'm not sure if that's the case. So let's start from the other side because we're not sure. So we got a 1. So we'll call this 2. That's going to be liquid plus, let's call it beta. This is clearly a single phase region. It's a skinny one, that beta. So if that's true, this has to be a 2-phase region, right? Because it goes 1, this is 1, this has to be a 2. If this is a line compound, it would go 1. I guess this would be now a 2-phase region, but you'd have 1, 2, 1. That wouldn't work because you'd have a 2 next to a 2. You can't do that. So this one, it's a straight line, but it's not a line compound. Can you have a binary line compound? No, you cannot. Other questions?
In the previous one I just labeled, where did that 80% come from?
Where did the 80% come from? It was hard to read here because I zoomed in on like the smallest possible portion of the diagram. But you would have done the lever rule, right? And we didn't do the lever rule because these were clear down here and we zoomed in, we couldn't see them. But we said that dot is about 80% of the way towards the solid. We ballparked it. Don't do that on the exam. Calculate it. And I will make it easy to calculate it for you. I keep forgetting your name.
It's okay, Jaden.
Jaden.
I was just thinking that the exam, I think the homework problem 3, that it asked us to label one of them and print it out. That one was a really good one because sometimes it's really useful to draw your horizontal line in a couple different places to really figure out.
Yeah. Let's pull that one up. Homework 3 was a good one because it had 2 vertical lines that were not line compounds, which is tricky. This one. Right? Wait, there's another one on this one? Oh, on the ice? This one? There's another one? No. This was the last one, wasn't it? Oh, this one. Okay, the only vertical line looking thing is this guy here. So is that a line compound? These aren't vertical. That one's not vertical either. Oh, that one. This is a line compound. We can test it, though. If we didn't know, we could test it. Right? We do our 1-2-1-2-1 rule. We haven't hit it from liquid yet, but the end members are always single phase, not 2-phase. By definition, it is pure some substance and pure another substance, so it's single phase. So we know this is something. Let's just call it alpha. Let's assume that that's not a line compound because it's got this big solubility region. It's probably not a line compound. It's probably a single phase region here. Right? Here, we can test that, though. Let's just assume this is alpha for a minute, okay? And the same thing over here. Let's assume that that's a solubility region for beta phase. So we've got 1 and we've got 1. That would make this a 2-phase region, probably, we think. Okay? So let's come back to it. Which would make this thing a 1-phase region, if that's not a line compound. So that's probably not the case. If you see a vertical, you assume... Yeah, but we can skip that for a minute. Imagine that's not there. You're coming from the other way. This is a single phase. That means this is a 2-phase. These are not vertical lines, so that's probably a single phase region, which makes this 2, which makes this 1, which makes this 2, not 1. That means this has to be a line compound. And at any point, you can pick lots of different temperature slices, like whoever was saying, somebody was saying, and you can verify these things. Like, okay, we think that this was a single phase region. Does it hold up at some other temperature? All right, let's try it. Liquid, 2 phase, still 1 phase, right? Holds up if it holds up at multiple temperatures, you know you're getting it right. Okay? Yeah, Sam?
How would you label that little teeny sliver of the line compound?
Okay, so let me use a fine point here. So let's assume that this line compound is alpha. I would label it with a line. I would not try and draw on it, right? And I would say that that is, whatever this phase is over here, let's assume that's beta. That's alpha plus beta. You look at what's left and right of it. On the left, it's the line compound. On the right, it's that beta phase.
And then would the one to the left of that line compound
Also alpha plus beta. What's the difference between those? Are they the exact same? This is also alpha plus beta. Are they the exact same? Its composition's totally different, right? You could have, I showed him this earlier, but let me draw this right here. Right? Imagine this. At that point, zoom in for a minute. If this is gamma, right here in the middle, and right here in the middle, in both of those points, you've got gamma plus liquid. You could have a 50-50 mixture, right? You've got 50% islands, 50% liquid in both of those points. But what's the difference? The compositions are totally different. Here, the gamma composition is whatever that is. Here, the gamma composition is here. Here, the liquid composition is that. Here, the liquid's that. So, totally different compositions. Even though they're both gamma plus liquid at 50% of each. Yeah, Ebza?
So the problem one of the homework was we had dotted lines. Were those also meant to be taken as
Oh, dotted lines mean uncertainty. Meaning experimentally they weren't sure, but you can treat it like it's a solid line. It means when you actually go and use this in the field, maybe it's wrong, but to the best knowledge, they think that those are flat lines. Yep. Those are good questions. I don't know your name. Lucas.
How do you find the composition again?
The composition? At any point, let's say you're right here, right? You can get the composition and the fraction of the phases with the lever rule. The lever rule will tell you the fraction, but to do the lever rule, you have to know what the compositions of them are, because that's where the tie line intersects the things to the left and right. So the liquid has that composition, because that's where it intersects the line of the liquid phase over here. And pure NB205 has pure NB205 formula. It'd be 100% NB205, whereas this would be almost 81% NB205 would be the composition of the liquid. So you tie the tie lines, and you see where they intersect some sort of boundary. Clarissa? Do whatever it's given in, unless I ask for the other, which is pointless, because that's just, it takes forever to convert, and this isn't a chemistry class. I want you to use chemistry, but I don't want to waste your time on a midterm doing chemistry calculations to the extent possible.
We don't have to know how to convert weight percent to 1%, vice versa.
You need to know how to do it. I'm going to try and not give you that because it's a time suck on a test, but you should definitely know how to do that. And sometimes it will be on a test. I just try and not, because it's like 10 minutes of wasted time. Ryan? What do you mean pair them with it?
It seems like any time we're at a paratectic point, and we're drawing microstructures above it and below it, they tend to be the same microstructure.
The paratectic above it and below it is the same microstructure.
No, I don't mean like above and below are the same. I mean at every paratectic point. You know, like how at the paratectic point for this one. I think it means like is there a pattern? Yeah, is there a pattern?
You gotta give me a little more specific.
So if you go to
Like this is a paratectic point.
yeah, so and if we were to draw a microstructure above it, it would be the liquid, the solid.
Yeah, let's say we're right here, okay? And we're going to go to right here. So just above it, we do the lever rule, and it would tell us that we're about 2/3 liquid, 1/3 solid, about. So we've got little islands occupying 1/3, 1/3, we'll call it alpha, the solid. You would be more exact. You would use the lever rule, and you'd tell me the composition. And then right here, what have you got? You've got about maybe 3/4 of this phase, we'll call it beta, and 1/4 solid. So again, the stuff that used to be liquid, and some of this is going to dissolve. So it's going to be just what we drew before. The island's going to shrink a little bit, and the rest is going to be beta, probably.
Yeah, so at this very technical point, the microstructures were similar to the microstructures we drew on the other phase diagram at that very technical point.
Yeah?
So is that the same for like all the microstructures, where at the very technical point you're going to have these two microstructures close together?
I guess, in as much as a paratectic reaction is always a solid plus a liquid forming a new solid, then yeah. Jaden.
On this same diagram, if you back up or like zoom out a little bit, between that line that you have labeled beta
Okay.
and the line compound on the y-axis, there's two regions that would be like that region and the box below it wouldn't have the same composition and the same alpha and beta. So like if you labeled the
Oh,
y-axis,
like right over here, this thing?
yeah, both those boxes are exactly
Yeah.
the same. Why are they separated by that?
So they're not the exact same as the short answer. It's tricky to talk about them now because we haven't talked about crystal structures much yet. Whenever you see something like this, when you see them labeled on an actual diagram, you'll see them labeled as oftentimes alpha, and sometimes that'll be alpha prime. What it means is that they're technically different crystal structures, but they're very closely related. That's hard to explain because I haven't told you the aspects of crystal structure. But let's say there's like an octahedral unit. That's like a type of building block. And in one structure, it's not distorted, but in another one, it's tilted a little bit. Otherwise, it's the same structure. That's what that denotes. That's a good question. Right now, just treat it like it's a different phase. Yeah, Rachel? Abigail.
So I just wanted to clarify something really quick to make sure I'm not messing up. So if we were to do the weight percentage, let's say at 40 mole percent of Me2O5 at around 1300 degrees Celsius,
Oh,
I wanted to compare alpha and beta and do the microstructure. Is it safe to assume that if I solve for alpha in weight percentage, then I can do 100
yes.
alpha?
Yes. Yeah, don't do the lever rule twice. Lever rule is for two phases. If you do it once, you know the weight percent of that phase, do 100 minus it for the other one. Save yourself some time. It'll give you the same answer if you've done it right. Tyler. Coarsening. What does coarsening mean? Coarsening means that, remember how we talked today at the end of class about, where is it? We talked about this phenomena with the copper and the aluminum, how you can go from this to that. Before it goes to that, these little things might just clump together and become larger precipitates. That's coarsening. It's the process of elimination of surface area by bringing things together, by growing. That's coarsening. We'll talk way more about it later this semester. Clarissa.
So do you form precipitates? Is that solely based on like how fast you cool it, or is there like a certain point when?
You can quench it. So let's say we're in this diagram. You're at 550 or whatever it is. So it's pure alpha phase. If you quench it really quickly, you might avoid the formation of these precipitates, even though thermodynamically they want to form. In fact, the students in my class, the week after the midterm, we're going to do this with aluminum and zinc. And you can actually quench it. It's supposed to be a two-phase region, but it's single phase because you dropped it into ice water. And then when you pick it up and you hold it in your hand, the little bit of thermal energy in your hand is enough for it to undergo the reaction. It turns into a two-phase region, and it's strongly exothermic. So you pick it up with your hand, that little bit of heat, all of a sudden it gets too hot to hold, which is pretty cool. So yeah, quenching it can prevent that. Carlos. Yes, I will have them up when I get home, as well as the video from class today, which I've already converted. This one's going to take an hour or two to convert. It's slow, but they'll all be up by sometime tonight, and the solutions. Ebza?
So on that problem one phase diagram,
Okay.
so going from the very top left corner, yeah, into the left box, that
Going from where now?
Top left corner, the 10% at 1800.
Here?
Yeah.
You cross a paratectic line, which means any liquid and some solid available will undergo the paratectic reaction. It's not the paratectic point. A point is at a point in space, but that line is anywhere along this line here, this dashed line, is the paratectic reaction, meaning if you have any liquid plus alpha that can turn into beta, it's going to do so, right? In this region, you've got alpha plus beta. There is no liquid there. Meaning even though you were at 10% above that, which had some liquid, you didn't go across the point, but you still went across the paratectic reaction, so you have no liquid left. It gets consumed.
So even though that was going to from, it's because the alpha was already present in the top level also?
Yeah, you had some alpha, so you're going to have some islands, right? But then you're going to turn into alpha plus beta, so it'll be the islands, but it'll be some beta between them. And I messed it up drawing a eutectic structure. It probably will not be. I messed that up. 40 minutes left. What do you want? I don't know your name. Simon. Yeah. Is that on the review? Okay. Calculating the change in theoretical Gibbs free energy for a reaction, delta RG naught, using Gibbs energies of formations from reactants and products. Okay. So for this one, for some reaction, let's write something. Let's say gasoline, right, being burnt. What's gasoline again? C8? What's gas? Gasoline is C8H18. So C8H18 combining with oxygen will form CO2 and H2O. And this is not balanced yet, so we need to balance it. So let's balance it. Let's add 8 carbon dioxides. We need to have a total of 18 hydrogens. Let's try 9. Are we balanced? Let's add up the oxygens. We need to have 16 plus 9. Am I messing something up? I'm right, right? So 16 plus 9, 25 math in front of people. So we need to end up with 25 oxygens over here. So we need 12 and a half of those, right? 12.5. Is that right? Did I mess anything up? That doesn't look right to me. I feel like it's right. All right. Let's assume that's right, that I didn't mess that up. How would you calculate the change in theoretical Gibbs free energy, which is just this thing? That is delta RG naught, right? The change in the theoretical Gibbs free energy is equal to products minus reactants. The sum of the products minus the sum of the reactants. So I would need to know what the Gibbs energy of formation is for CO2, H2O. O2 is what? 0. It's elemental. It's basically saying what's the change in free energy going, if you start from oxygen and turn it into oxygen? There's no change. It didn't change. So there's no change. And then C8H18. So I'd need to look those things up. Let's just write them out as if we knew them. It's going to be 8 times the Gibbs free energy of formation of CO2 at the temperature of interest plus 9 times the change in Gibbs free energy of formation for H2O at whatever temperature it's happening at. Give ourselves some more space. Minus 1 times the change in Gibbs free energy of C8H18. And we can ignore oxygen because it's 0. Straightforward? Yeah, you have to know those, so I'd have to give you those. Okay? Any questions on doing this? It's just products minus reactants, unless I've messed up. I don't think I have. I forgot your name already. Chase.
Can we do that again using the partial pressures?
So partial pressure doesn't come into delta RG naught. It's when you want the total change in energy that needs both theory and experiment. So let's do this with partial pressure. Now we're going to calculate delta RG, and we know that that's equal to delta RG naught plus RT natural log of Q. It's a terrible natural log. Natural log, okay? Everybody with me? How do we calculate Q? Q is it's going to be the partial pressure of the gas in a specific way. Products over reactants, right? Products over reactants. So it's going to be, what are our products? It's gas of CO2, partial pressure of CO2, and the partial pressure of water. And those are raised to the number of coefficients they are as an exponent. So 8 and 9. So 8 and 9. This is a little bit close. Then we divide that by the reactants, right? If these were all gases, and I don't think the gasoline is a gas, even when it goes through the injector, I don't think it's a gas, it's probably a liquid, so we can probably ignore it. So then all we need is the partial pressure of oxygen, PO2, to the 12.5, which still seems wrong to me, but if that's right, then you'd raise it to the 12.5. That clear? Premit?
So all the partial pressure
It depends on what I'm asking. I can have you solve for them too. Yeah, you can work these problems lots of different ways, right? I could say at equilibrium, and the magic word when I say equilibrium, you say this is 0. The change in the reaction is not happening. It's at equilibrium. I could say at equilibrium, you solved for this previously. I could say, if you know these two things, what's the partial pressure of O2? And you could solve for Q, and once you know Q, you could solve, since you know these two, you could solve for that. But yeah, there's lots of different ways you can frame this. I could give you these values, and I could say, given this and given these values, will the reaction go forward or backwards? And you'll see whether this is a positive or a negative number, or lots of other things. Yeah? Yeah, what's your question? I don't know your name. Evan?
Yeah. And so, will you be giving us the free energy or the compounds?
I think I give one of each. I think I give you one where I give you the formation values, and you calculate the delta Rg naught. And I think on another one I do Hess's Law, where when you combine Hess's Law together, the formation of the reaction, there's only one product, and so you know what the formation is of that product. So you calculate it using Hess's Law. I think that's the two that I wrote on this test. Jaden.
Are you going to give us constants, like the gas constant and stuff like
I think they're on the test, but you should definitely write those things on your note sheet. I'm pretty sure I put them on there, but double test. Is that your question, Chase? Shujang? One more time? Jingchang? Jingchang. Oh, so very common mistake. Good. I'm glad you brought this up. One of the most common things where I see people get questions wrong here is these are commonly with the units of kilojoules per mole, because the amount of energy for a whole mole of substance is pretty large, and so they often do it in kilojoules. But this is 8.3144 joules per mole. So you cannot add a kilojoule to a joule and get the right answer. You need to put it all in kilojoules or all in joules. It doesn't matter which way you do it, but you have to be consistent. Otherwise, you're going to get that wrong. You told me, and I forgot already. Victor. 8.3144, that's joules per mole Kelvin. Jare. Nope, I'm not going to make you do that. In other words, the partial pressures, these need to be in ATM, and that's all I'm going to give it to you with. I'm not going to make you convert those. Other questions? So there was more up here. We did change in Gibbs free energy. Calculate the actual change in Gibbs free energy for a reaction combining theory and experiment, accounting for partial pressure. We did that. Know what the signs mean. Any ambiguity. A negative sign is spontaneous for free energy. A positive sign is not. Just the opposite for voltages. A positive voltage is spontaneous. A negative voltage needs to be provided. A negative free energy, yeah. Well, by good you mean spontaneous. Yeah. Yep. Not on this test. I hope you understand that, but I'm not going to test you on it. Other questions I can answer? Question? If it's free energy, positive means from your starting point to your final point, I guess for you guys, starting to final, you went up in energy. So it's not favorable. It's not spontaneous. From a voltage standpoint, it's just the opposite. A positive voltage is positive. It provides that voltage automatically. A negative you would have to provide. Degrees of freedom, sure. It's not on the test, I don't think. Yeah. You can hit delete, but it might come back on the final. I'm forgetting your name. It's like the third time. Chase. I have 2 Chases, and you look vaguely alike. Vaguely. All right. Sure. Yeah, the voltage. So I'm going to call it overall cell potential. If you've got 2 reactions, a reduction and an oxidation, let's assume some crazy battery. Let's assume that you've got magnesium 2 plus 2 electrons, giving you magnesium metal, right? And then you've got silver plus 1 electron, giving you silver metal. We could calculate the voltage that this battery would give us, right? It's going to be big because silver is way up there positive. It is positive 0.8 volts, right? And magnesium is clear down here at negative 2.36. So 0.8 and negative 2.36. 0.8 volts and negative 2.36 volts. Yeah, right now these are both written as reductions. So we cannot add them together for a voltage because we don't have a complete electrochemical reaction. A chemical reaction has to be balanced. So one of these has to get flipped, and it's the lower one. The more negative one gets flipped. Because then when you add them together, you get the biggest positive number. Right? Therefore, it's spontaneous. Ebza?
Does that apply for both the standard reduction and standard oxidation values?
If it was a list of standard oxidation, you would still want to flip the more negative one. The only difference is that in this one, the lower one goes from reduction to oxidation. If it was an oxidation table, it would go from oxidation to reduction. But still, the more negative one you flip. So when we flip it, now we've got silver metal reacts to form silver ions plus 1 electron. So if you add these up, and that's a positive 2.36 volts, if you add those up, the electrons don't cancel, right? So we would have to do the following. We'd have to multiply this bottom one by 2. Yes? Dadgummit, you're right. Yeah, you're right. Thank you. Thank you so much, Eric. Thank you. Good catch. This is positive 0.8 volts. This is negative 2.36 volts. Thank you. We would have gotten that wrong. So we're going to flip the more negative one, which is now going to be magnesium metal, yielding magnesium 2 plus ions plus 2 electrons for a positive 2.36 volts. We still need to multiply this by 2, though. We do not multiply the voltage by 2, though. It's not like on a per mole basis. It's just like a fundamental material property. So that leaves us with 2 Ag plus magnesium metal yields magnesium 2 plus 2 Ag. And the overall cell potential, delta V naught, is some math, 3 point something, whatever that is. Jaden.
So the reason we flip the more negative one to get a positive number is because if it was negative, the reaction would progress in the opposite direction.
Right. If you, for some reason, got this wrong, when you added these two things together, they would both be negative, and you'd end up with negative 3.16, and that would be incorrect, whereas we have now positive 3.6, so we know that the reaction as written is spontaneous. Now, this is only on paper, right? When you take into account the actual voltage, delta V, the measured voltage if you had an instrument to measure it, we know that delta V is equal to delta V naught minus, not plus, minus RT over NF, and they usually do it in cursive, natural log of the concentration of the oxidized species over the concentration of the reduced species, or products over reactants. And then on this one, we have to do one slight modification. Because our reduced species has a coefficient of 2, then we need to put a 2 exponent right there. Okay? So if I gave you the actual concentrations of magnesium 2 plus, silver 1 plus, the temperature, you could actually tell me what the overall voltage is. It's going to be probably pretty close to this unless we've got some crazy difference here. It's probably going to be in the neighborhood of 3 volts. Abigail?
So for the overall cell potential,
Yep.
You didn't times your silver by
Yeah. Yep.
you times it by 2 down in the delta V
No, I did not.
MR squared? Or am I thinking of the wrong idea?
With free energy, you would multiply it, but with voltage, you don't. Voltage is like it's a fundamental elemental property that to add or remove electrons, there's just a voltage associated on an element basis. It doesn't change with amount of substance. The voltage is still defined by the element chemistry, not by the amount.
Where did this MR squared come from?
Oh, so the concentration of the reduced species, this guy got reduced, and it had a 2 in front of it. So it got raised to the 2 power here. Just like the reaction quotient Q, we took the partial pressure raised to the number of coefficient. Same thing here. So many hands. Mina.
What is the difference between when we get a negative cell potential and a positive cell?
A positive cell potential here means that's the battery that it's spontaneously producing. That's the voltage that the battery's producing. If this turned out to be negative, that means that you're pouring that amount of energy in to make the reaction go as you've written it. Positive is spontaneous. Yeah. Yep. I don't remember. Michael.
What is that N?
N is the number of electrons in the reaction, which for us is 2. We had to multiply that one by 2 to get 2 electrons on each side. That might be 6 or some other goofy number depending on what I give you. In this case, it's 2. And F is Faraday's constant, 96,500 coulombs per mole. Sam?
So this is the standard reduction potential,
Yep, these are standard reduction potentials.
and that is saying the most negative one is the one that is going to give the most energy. What is that?
Well, what it means is we can put any 2 of these things together, but these are all written as reductions. And a redox reaction has both reduction and oxidation, meaning one of these has to get flipped. And you flip the one that's more negative because then it becomes a positive number, and when you add it with any other number above it, you get a positive outcome.
So that's saying when this is oxidized.
The lower one, in this case, gets oxidized.
Yeah, it's going to be positive.
Yeah, that's right. That's right. Because it's written as a reduction right now. And if this was a oxidation potential, if it was metals turning into ions plus, the lower one would still get flipped, but that means it becomes reduced as opposed to oxidized. Lucas?
What is the physical meaning of delta V?
What is the physical meaning? So if I literally take a voltmeter, like remember when we lit up the LED in class? You saw the LED light up because it produced a voltage. If we took that same stack of pennies and I put a voltmeter on it, this is the voltage I would read. It's the voltage that it produces. And again, this is still on paper. Like in practice, there's lots of things that can make it be less, but for an introductory class, that's the voltage you'd expect to see. Ryan? Two. Right? The magnesium had 2 electrons. We multiplied silver by 2 in order to go from 1 electron to 2. Total electrons is 2 on the reactant side, 2 on the products. It's just 2. Nope. Nope. It's 2 electrons involved in the redox reaction. Xinjiang? What's this happening here? So in free energy, this was Q, right? And it was the partial pressure of the products over the reactants. It's the same thing here, except instead of gases, we have dissolved species. So you take the dissolved products. What's our product? If you look at it, that's our product. You have a solid, which we ignore. This is a product, so it's the concentration of that. This is a solid, so we ignore it. This is a dissolved ion, so it's over that squared. So it's still just products over reactants. Because it has a 2 in front of this silver 1 plus. That's why it's squared. Other questions? Yeah, Ryan?
So if the 2 is from in front of the silver, what if it was like O2?
O2.
It was like a subscript. Would you still count those, or would that still count? You know what I mean?
So you're saying, like, what if instead of silver we had something goofy, like, this doesn't exist, but like a chlorine 2 plus? It doesn't matter. You ignore that. It's just the coefficient. That doesn't exist, by the way. Yeah. Other questions? We got 20 minutes left. Yeah, Matt's sister, Claire. Okay, her question was, if you have some reaction, you calculated this, you calculated that, you add it together, and this turns out to be negative, it means that you can take the reaction as you wrote it, flip it, and make that a positive number. It means that you had it backwards. Or you could write it as is with a negative number, but I'd hope that you would understand that to make the reaction go as you've written it, you'd have to apply a voltage. It's not going to spontaneously do it. Yeah, if you switched it, then it would become positive, meaning it would provide that voltage. If this turns out to be negative, you have to drive that. So when they separate copper at Kennecott, they're providing a voltage to drive a reaction that wouldn't happen on its own. But they do that because it plates out pure copper. Otherwise, copper wants to mix with all the other horrible things in it that we don't want because of entropy. But we overcome entropy by plating it at a certain voltage. Could you switch what?
Like if you switched it, and then it was still negative, is that possible?
No, because if how it's written produces a negative voltage, and you switch it, then you just switch the sign of that. So it can't be negative both times. Is it Noah? Noel? 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 Noel. All right. What else? Yeah, Ryan?
Can we hurry run through the definition of like eutectoid and peritectoid?
Yep. Let's do those real quick. Key reactions that you should know. Eutectic, peritectic, eutectoid, peritectoid. And there's others, but for this class, for this test, you just need to know these four. And eutectic is a liquid going, upon cooling down, into two different solids. A peritectic is a liquid plus a solid turning into a different solid altogether. A eutectoid is a solid turning into two different solids. And a peritectoid is two solids turning into a different third one. What else can I help with? We've got the 1-2-1-2-1 rule. All right. I don't remember. Matt? Ben.
Did you write all of those in terms of cooling?
Those are always in terms of cooling. That's how they're defined. Otherwise, these two are the same thing. Eutectoid and peritectoid are the same thing if you didn't take into account cooling. What other questions you guys have?
What about the different
Prefixes. Oh, okay. Hypo means not enough of something before some event. And hyper means too much of. So if you're talking about a eutectoid composition, if it's hypoeutectoid, that would be a composition before the eutectic composition. To the left of it, lower. Hypereutectoid would be greater than the eutectoid composition. What about proeutectoid? That means it happens before the eutectoid as you're cooling it down. So a proeutectic phase or a proeutectoid phase would be something like if you cool down right here, I'd have to actually be over here. On that one, I'm forming proeutectic, what we called alpha. But if I go through this reaction, the reaction is liquid is to alpha and whatever this is, let's call it beta. I'm forming proeutectic alpha ahead of time. It's before it. Ebsa?
So, does all the proeutectic stuff get converted to plastic eventually?
No, not necessarily. So I think we've got a picture of this in chapter 10. I think we've got a picture of this. Pro-eutectoid steel. So, yeah, right here. Okay? In this one, this is an actual microstructure. Like, we've been drawing these really idealized circles. In the real world, they look like this. But you see that there's like these big globs of the white region, and then there's the white in like the zebra pattern. This big glob, that's some of the ferrite that formed prior to the reaction. That's why it globbed up rather than being all zebra-like in small layers. This was ferrite that formed before it all had to happen instantaneously. So this stuff could happen slowly as you cooled it down. Everything else was basically austenite that had to quickly switch into ferrite and cementite. So that's what it would look like, is a big glob of it. On the homework, there's a good example, right? On the homework, you saw this really clearly with tin. On this one, yeah. So you can see really clearly here, this was a sample our students made, actually, in a lab class. Here's the zebra stuff, but you had a great big glob of not zebra stuff. This was pro-eutectic, either tin or bismuth. Since this is an SEM and it's the darker one, it's the lower Z number one. Probably that'd be tin, I guess, whereas the white would be bismuth. But see how there's like big globs? This is your pro-eutectic phases, and it's still there even though we cooled it down. It's just that all the liquid then had to rapidly convert to tin and bismuth-rich regions. Okay?
But you're not losing mass, though.
Losing mass, what do you mean?
You started at 13 kilograms, went down, not.
Oh, you still have 13 kilograms, yeah. Yep. Chase?
Yeah, I was just going to say, when we look at what the percentages for each of those were, is that on?
I'm going to post the solutions tonight, but they're right here. It was like 50-50-ish. It was somewhere around 50-50. I can pull it up. And what's interesting, you could do it two different ways, and you get the same answer both ways. For example, if you do a histogram, and you say, just tell me everything that's white in this picture, how much is it? And you calculate it, versus doing it based off of circling these pro-eutectic regions. Technically, you could do two different lever rule calculations, but the initial composition should be the same for both of those, and you get basically the same answer. For both of them, I get, so for one, if you do the histogram with just the total amount based off the lever rule, it's 46.53, and this way it's 48.52. This is pretty amazing. That's pretty flippin' amazing that this works. You guys don't look amazed. It's amazing. Everyone know how to use ImageJ software? I promise that will not be the last time you use that. Maybe you did it in Photoshop. That's fine too. Photoshop makes it easy. ImageJ is not bad though, and it's free. So if you ever need to do this and your student license dies for Photoshop, or you don't want to download it illegally, whatever the case may be, ImageJ is free and easy to use. And I've got a sweet tutorial that Christian made, an old TA. What else? Yeah, there we go. Yeah, so favorability can best be described kind of graphically. Let me show you. So favorability, you've got your reactant turning into a product, and you have two options. You're going to start out here. You can either go down in energy or you can go up in energy, right? If your change in energy, your final minus your initial, if that's a positive number, you went up in energy, so that's not going to be favorable. The universe never does anything to go up in energy. It only goes down in Gibbs free energy, right? So that's a negative change. If you go down in energy, then final minus initial is a negative number. Negative is favorable. Make sense? That's why we keep saying negative Gibbs free energy is going to happen on its own, just because the final state is lower in energy. It went down. Burning gasoline with oxygen goes down in energy. Yeah, Ryan?
Other than Gibbs free energy, is there any other values that show favorability?
No. Gibbs free energy combines entropy and enthalpy. You could treat those separately, but it would be wrong to because there's exceptions. Enthalpy could tell you, oh, it's going to happen, but entropy, like in a rubber band, throws you off. Or vice versa. Entropy could say, oh, it's going to happen, but bonding. So that's why we use Gibbs free energy, because it combines those two interesting things together. What else? We got 10 minutes. Yeah, Xinjiang. A pro-eutectoid. Yeah, that's steel. If we go back to steel, we see that really clearly. Pro-eutectoid means it happens before a eutectoid, and eutectoid is one solid turning into two. So right here, we have austenite, and if you cool it down, that's the eutectoid point at 0.76 there, at 727 C. It turns into two phases. So pro-eutectoid means that you form something before that reaction. So if you cool down right here, for example, the second you touch that red line, you start to form pro-eutectoid ferrite. Or over here, if you cool down on this, when you touch that red line, you start to form pro-eutectoid cementite. Meaning, eventually you're going to form ferrite and cementite in the actual reaction. Pro means you're starting to form some of that before the reaction. Chase?
And just real quick, the main distinction between those two different eutectides would just be structure, crystal structure, right?
To the left and to the right? Yeah, it means the phase that's along the grains, is it cementite or is it ferrite?
Well, no, I mean like between the pro-eutectoid and then the eutectoid.
Oh, yeah. Well, one is pure, and the other one is a mixture of these layered of cementite versus ferrite. Other questions? You guys supremely ready for this midterm? If you can show up a little bit early on Friday, that'd be great, because we will have assigned seating. It'll take just a minute to shuffle. Don't worry, I'll make sure everyone gets a full 50 minutes on it. But if you can get here a minute early, that would be helpful. Ryan?
So those microstructures are for the pro-eutectoid and after, right?
Yeah, this is showing you pro-eutectoid, I don't know if it's alpha, it could, whatever one of these phases. And this is what it's probably going to be because it's at a high temperature. If this was at a really low temperature, it might be a dispersion of precipitates instead. No, after the eutectoid, all of this austenite would be zebra stripes. Because that is what the eutectoid reaction does. It says all along here, austenite turns into ferrite plus cementite. It like hides it behind the image or something. Yeah. What is this one, are you asking? That's austenite with something along the grain boundaries, either ferrite or cementite, meaning we're still above the eutectoid reaction. Okay, if you've got other questions, there's a whole other TA session tomorrow from 6:15 to 7:45, I think they said, in this room. You can send us emails, use Piazza. Otherwise, we'll see you Friday.